we have discussed about what is superconductor, properties of superconductor, as well as the basic theory working after the superconductor, that includes BCS theory and London penetration gap. Now we are moving to the last phase of the chapter, that is applications of the superconductor. In this application, we will discuss about the three parts. First, it will be depending on the Maglev. Second, it will be depending on the Josephson junction. And the third part, we are going to discuss about the right arm. Now, let's start. So, first, the word Maglev. Now, what do you mean by Maglev? Maglev stands for the terms magnetic levitation, and it defines as it is a process by which an object is suspended above the another object with no other support in between, okay, except the magnetic field. Now this magnetic field actually is invisible, so you will be thinking that that is nothing but it is levitating on another object. Okay, this you can see down there. We are taking a superconductor, we are placing in a liquid helium, okay, so that will convert the normal conductor into superconductor, okay, and when we are placing a magnet on it, it is actually levitating. Now what is the reason after that? The reason is nothing but the property named as the Meissner effect. Now, what was the Meissner effect was doing? Actually Meissner effect was expulsion all the magnetic field that was externally provided to a superconductor. Now, how does it do it? We can see that in the superconductor what is happening, a north and south pole is generated, okay. Similarly a magnet is also having a north and south pole, so it generates exactly the like poles to it. Now we know that the like poles actually repulse, and because of this repulsion it starts levitating on it. So this is the basic concept of the magnetic levitation. Now with the help of this magnetic levitation we have got many applications, in which of them is a maglev train. Okay, so now the first train that will be discussed, or the technique we will be discussing, is EMS, and EMS stands for electromagnetic suspension. Okay, basically electromagnetic suspension is utilized in the German train. And how does it work? You can see that what happens when the trains are there, okay, running, that has got the base and train. Here we have got the two part. In the base you have got the electro for motive force, that is the EMF will be generated with the help of the coil, and just above a magnet is utilized. Okay, so you can see that magnet and electron here. So electricity pass through it, magnetism is generated, and exactly like poles are generated. Because of that, what will be happening? It will start levitating, and that is, this lift is almost of 10 mm. Okay, and the net you will be getting of the 150 mm of levitation. So this is how the things work. Okay, that is in the EMS. Now the next second part, in that, how, see, maglev, the levitation is done, but you need the train to get accelerate as well as deaccelerate in the term of traveling from one place to another. Okay, so how does that happen? You can see that in that what happens, we know the basic fundamental. The like pole will be repelling and the unlike pole will be attracting. So you can see that the south and the south pole will repel each other, but in the similar way the north pole will attract it. So what will be happening? Your train will moving slightly ahead. Okay, but the thing is that this is only the one time it is happening. So to keep it in motion or in motion, what would be the scenario? The scenario would be that this alternate would be there. So this north and south pole would be alternated, and because of that, the moment it moves to the north, okay, you can see that the front part north moves ahead. At that time, what is happening? The south is attracting it, and north pole is repelling it. But now when it moves forward, that field would be now alternate. Now that south will become north and north will become south, and because of that this train will be moving forward. This you can see that what happens in the attractive force, okay, in the side lines, this foil you can see that it is alternating, and this alternating field will move slowly and eventually the train ahead. And if you want to deaccelerate the same, so just the opposite logic would be working in the same. So this is the logic of the acceleration and the deacceleration of the train or the maglev trains. Okay. Now we'll go with the second part. The second part is nothing but the EDS, and it is another system that stands for electrodynamic suspension. Okay. Now this electrodynamic suspension utilizes the superconductivity. Okay, in that, what will be the scenario? In that, we are taking a superconductor, and to make a normal conductor a superconductor, we will cool it down. So once we get this cool down superconductor, we will get it on the side of the train. Okay, now what will happen? The superconductor is there, and this side magnetic field is there. So basically, what will happen? This north and south pole would be there. So north and north pole will repel, and south will attract. And because of that, there would be some levitation in the same. So you can see in the diagram, this north and north is actually repelling it, and south is attracting. So this repulsion and attraction will actually levitate the train above at the certain level than the track. Okay, so this is basically an EDS system, and that is working through the entire train. Track is that. So you can see that in entire track that was present, and this is how it will be moving ahead. Okay, so this was about the maglev and magnetic levitation and the two system EMS in the EDS. Now the next function is the Josephson junction. But before we start with the Josephson junction, let's understand basic things. So if you are taking a particle, okay, and it is dashed on a voltage barrier that is having V, and the energy is E. Now, what happens in the classical theory? If V is greater than E, that is energy with the particle, what will happen? It will get repelled back. Okay, you can see that it is dashing and coming back because it is comparatively less. Okay, it needs equivalent energy or more than the equivalent energy of V. But that doesn't happen in the quantum tunneling or the quantum effect. The quantum tunneling, or you can say that quantum effect, what will be the scenario? This particle will tunnel out through the barrier, and this effect is known as quantum tunneling. Now, the Josephson utilized the same theory. What he did, he took two superconductors, right? And in that two superconductor, he just separated it with some distance, and instead of that, he used the insulator in middle. Now, insulator here can be the perfect metals, okay, with insulator, or normal conductor will also behave here as an insulator with compared to superconductor. Okay, but what he observed, because of this quantum tunneling, what was happening, these particles or electrons, we can say that in our context, it was actually tunneling out through the insulator. So basically, there was no difference. Easily, your this Cooper pairs were actually traveling from one end to the another. This was the study of the Josephson. So it was defined by the Grand Josephson in 1962. We observed this in 1962, and it also called as SIS, SIS, superconductor, insulator, and superconductor. So they were understanding when this distance of the insulator, okay, is approximately till 1 nanometer, then this phenomena is happening. If it is more than that, then across some voltage or potential difference would be definitely there. But the moment it goes 1 nanometer, what would be the scenario? It will be allowing to easily flow through it without any drop in the voltage. This was basically Josephson junction. Now, we have got the two type of the effect, DC Josephson effect and AC. We will discuss first DC. So in DC Josephson effect, what is happening? We are not providing any voltage difference. So what happens? This electrons, okay, the electrons travel easily and flow through it. So you can see that it is flowing through it, okay, without any voltage drop. Now this happens until this current is below the critical current. Once it rises up, this effect is lost. So this is basically DC Josephson effect. Now we are saying we are taking the same apparatus. Okay, when we are taking the same apparatus and just getting the voltage, or we are providing some potential difference to it. Now, when we are doing so, what happens? The electron will be generated from the voltage source, okay, and it will travel through it. It will make Cooper pair, and then it will flow through it. So, meanwhile, what happens when it is actually traveling? Okay, so you can see that when it is traveling from the voltage source, it is a single electron. But the moment it enters the superconductivity, Cooper pairs are generated. And when this Cooper pair goes through this insulator, what happens? There is some force applied on it. And because of that force, what is happening? It starts oscillating. Okay, you can see in the above diagram that it travels, the Cooper pair traveling, and because when it travels from one medium to the another, that is insulator to superconductor part 2, what is happening? There is some oscillation. This oscillation generates a AC effect. So now the particle would be having the frequency F equals to 2 EP by H. So this would be the frequency of the Cooper wave that are traveling. Okay. So this was your AC Josephson effect. Now utilizing the same, you will be giving on the application of the Josephson effect, that is squid. Now it is not that squid, that is a marine life animal, but comparatively it stands for superconducting quantum interference device. Now you can see that it is a superconductor exactly because it's having a Josephson effect. Along with that, quantum interference. Now use the word quantum stands for the tunneling effect. So now everything would be familiar to you guys regarding this entire terminology. Superconducting, quantum. Now there will be some sort of interference in this device. Okay, we will see what is in the terms of interference. So basically what happens when you are taking this fluid, okay, so basically it is combination of the two Josephson junction. Okay, so when you are taking the two Josephson junction, you can see that in the middle part, there is an insulator. On the from the both the side, what is happening? The current is flowing through this. Okay, so when the current flows through it, you can see that it will be basically divided into the two parts. Okay, so equal to part, that is current is divided into two. Okay, but this happens until some external magnetic field is not there. The moment when some external magnetic field with flux comes, a current density is induced. So you can see that in the upper layer it will be forcing against, and the lower it is adding on. Now because of this difference in the current, there would be the change in the voltage. So you can see that with the help of external magnetic flux, the voltage difference is generated. Okay, and this is the basic application of the squid. It is used to measure the Earth's magnetic field and the biological currents. Now we know that the biological currents are extremely low. Okay, so to detect these changes, it can detect as small as 10 raised to minus 15 volts to 10 raised to minus 21 Tesla. Okay, so basically it is utilized to get or detect a smallest change in the current with the means of the magnetic flux. So this was all about the squid. Now we are moving to the next application, that is a gyrotron, and it was given or it was actually founded by Alan Turing. So before we start with the gyrotron, let's understand some basic thing. Okay, so we know that there is a simple application we are taking. We are taking a battery and we are taking a bulb that is glowing. Okay, and in middle we are going to switch, or you can utilize here as a fuse. Now what is basically function of the fuse? Now fuse works until an external amount of the current is not increased. Okay, so by any means, when our source is generating extra current, our device doesn't get damaged out. Because of that, we are utilizing the fuse in the middle. So if by chance some extra current or voltage is induced, this fuse will go off. Okay, and it will save our device. This is the basic, nothing but the circuit breaker. It is also known as a circuit breaker, and that is the application of the cryotron. But it utilizes the superconductivity in the same. Okay, so you can see that now here we have got the two arrangements, or in the apparatus we have got the two things: a straight wire and the coiling is there. But this coiling is done surrounding the straight wire such that there is no physical connection between them. Okay, so that the straight wire is of tantalum and the surrounding wire is of iron. Okay, now both are getting into the superconductivity state. We are cooling it down such that what is the basic criteria for that? The critical magnetic field of tantalum would be comparatively smaller than HCB. Okay, this is the basic functionality of the same. Now what happens when a small current flows through this? Definitely a magnetic field would be generated. Okay, but it will not affect it. But the moment some external magnetic field becomes more due to more amount of the current flowing through it, what would be happening? It will get lost the superconductivity of the tantalum wire. Because of the same condition, if the HCB is increased compared to a certain more value, it will loses out the superconductivity of the pendulum. Now, when this pendulum wire loses the superconductivity, it will work as a normal conductor. So, when we compare a superconductivity flow with respect to the normal conductor, definitely it would be having some resistance in the conductor, and automatically your current, what will happen? Current will reduce. But after that, again, when the normal condition prevail, again your superconductivity will be maintained, and again the normal flow will start. So in this manner, we are utilizing the fuse. Now fuse actually automatically starts again. We don't have to replace in this case. Okay. So with the help of the small current that is flowing through this coil, we can control the larger current. So it is actually controlling our entire gateway. So this was all about the applications of the superconductor. Here we finished up the entire chapter of the superconductor that consists of the 17%. Okay. So hope you guys have understood well. Stay tuned. See you in the next one.